strategy is called integration by parts. It is basically an integral strategy that you can use to undo um, derivatives that are created by products. So for example, if I show you here, just to refresh your memory, let's suppose I just wanted to get the derivative of f of x multiplied by g of x. I'm just going to back up a second. All I'm showing you here, don't worry about trying to write all of this stuff down if you're trying to take notes. At the bottom of this, there's going to be a formula. Integration by parts is nothing more than a formula. I just wanted to give you some context of where the formula came from, which is what this first little blurb is going to do here. So if we had f of x and we multiplied by g of x, the derivative would be product rule. Derivative of the first, so the first being f of x, so f prime of x, derivative of the first, multiplied by the second, plus the first, multiplied by a derivative of the second. That would be the notation that we'd use to represent product rule on f of x times g of x. So knowing that integrals undo derivatives, if I took the integral of the right side, which is what I have written right here, it should give me what I took the derivative of. So the integral of that right side, which is where I am right here, would equal the original product that I started with. Well, to develop this formula, what mathematicians did is they then kind of played around with this and rearranged things a little bit. So they took the integral of this sum, just separated it into two separate integrals. Then this term, f of x, g prime of x, d of x, they isolated that by itself, and they took this integral, get my highlighter out here, they took this integral right here and moved it to the other side. Like so. Over to there, and that's how this ended up over here. That is, and they changed the order of it. They called it g of x, and then they put f prime of x second, but this right here is just this term moved to the other side. Now, if we're going to try and memorize that in itself as a formula, that's going to get pretty confusing with the f of x's and the g prime of x's. So they use a u and a dv notation that will look like this. So they let u equal f of x. So f of x here is going to be u. They let du be f prime of x dx, which is over here, f prime of x dx. So that's going to be du. We said that u is f of x. V is going to be g of x. G of x is right here and right here. And dv, which would be the derivative of g of x, is going to be g prime of x multiplied by dx. And that appears right here. So if I take this substitution that you see here and I rebuild this mess up here, you end up with a formula that is used for integration by parts. So what you see here in this purple box is the formula that you're going to need. The integral of u dv is equal to uv subtract the integral of v du. And that was developed by kind of taking a product rule, twisting it around, and turning it into this formula here that's used in integration. Yeah, it's called integration by parts. This is what students need to memorize, what they need to know. Okay, so going forward with the rest of these examples that I'm going to get into, this formula is what we're going to use. Okay, so if I go here now, here's the goal of integration by parts. In the formula, so when you look at your formula, so the integral of u dv is equal to uv minus the integral of v du. You can see that in the formula, there's an integral. Well, here's the goal of integration by parts. You want to start out with some integral that you're kind of stumped with, that you can't do just by inspection, by looking at it. And then you want to, through this formula, generate an integral that's in this formula that is less complicated than the one you started with. So sometimes if you pick the wrong substitutions for the u and the dv, this will turn out to be worse than what you started with, and they say, oh, that's not a very good substitution, I better start over. So the key is, whatever you decide to let u equal, just reading here, you want to make sure when you take its derivative that it is less complicated than what you started with. The reason you say, well, why is that? Because in this integral, you'll notice du is going to appear. Well, if du is more complicated than u, that probably means this integral is going to be more complicated than this integral. But that's the goal of integration by parts, to substitute into this formula so that the integral you create in the formula will be less complicated than the integral that you started with. Now, sometimes it's really, really obvious what to let these things equal, and then sometimes it's less obvious. So they'll start out pretty straightforward. Let's have a look at this first example. The first thing is you say, well, how am I going to know that it's integration by parts? There's no easy answer to that, unfortunately. Sometimes it's just practice, lots of experience doing them. You say, oh, I remember doing one like this before. It was integration by parts. Often you're going to be dealing with a product. So I see here x and not natural log of x dx. So that's kind of the giveaway that, and it's not a situation where in the last section, if I let u equal ln of x, well, then there would have been a 1 over x somewhere. The du would have shown up in the integral. So that isn't necessarily the case here. So what I'm going to do is set up two substitutions. You got to take this original integral and you have to arrange it so that you're going to let u equal something, and then you're going to let dv equal something. These two combined have to make up this integral. So you can't use part of it and say, oh, I didn't use that part for either of these. Part of the integral's got to be u. The other part of it's got to be dv. Now you got to choose which one it is. Here's the key. In our formula, I'll just jot it down over here again. The integral of u dv is equal to uv minus the integral of v du. Well, in the formula, I'm going to need to use du. Well, to get a du, I'm going to have to take the derivative of u. In the formula, I need a v. Well, if I have dv and I need to get v, I need to take the antiderivative to get what v is. But one of the important things is that you must make sure whatever you decide to let dv equal, you need to be able to take its antiderivative so that you can get v. So for example, here, I would not want to let dv equal ln of x. And I'll write it down. You say, well, why not? Because now the next thing I need to do is figure out v. Well, the way to find v is to take the antiderivative of that. Meaning, can you think of something off the top of your head that when you take its derivative, you get ln of x? No, I can't think of anything. It's not one of our rules. So for that reason, I'd say, well, that's probably not a good choice for dv. How about we go with let u equal ln of x, let dv equal, so I've used up ln of x for the u. The dv will always have the dx with it. So the only thing left there is the x and the dx. They're going to go here. Now, to get the other elements of this formula, I'm going to get du. I'm going to take the derivative of whatever I chose to let u equal. So du will be 1 over x dx. And v is going to be the antiderivative of this. So the antiderivative of x is x squared over 2. Now, don't put any plus c or anything like that in here. Okay, so we're going to take this information. This is the integral of u dv. I've split it up down here into u and dv. And now I'm going to fill in the formula. So the formula is uv, so u and v, so x squared ln x over 2, that's uv. Subtract the integral. Now here's the thing I'm looking for. I want this integral to be easier than what I had here. Hopefully it will be. What do I need? The integral of v du. So here's v, here's du. X squared over 2. There's v. Du is 1 over x dx. Well, we're going to clean this up and see if it is better than what we had. Equals x squared ln x over 2. So I have a constant of, so this is all a product, so I'm going to bring the 1/2 constant out front. Integral. I have x squared over x, that just reduces to x over dx. I think you'd agree that the integral that I generated in the formula is easier than the integral that I had to start in the original question. So now I just continue. Note, this is not an integral, that's part of your answer. So x squared ln x just keeps coming along for the ride. Minus 1/2. Take the integral of x dx. That'd be x squared over 2. Now you can put your plus c, And your integral, this is your final answer, x squared on x over 2 minus 1/4 x squared plus c. There you have it, an example where I have done integration by parts, and integration by parts again relies upon you knowing the formula. The integral of v du, of u dv is uv minus the integral of v du. And the key then is for you to make sure you select the right components to represent each of those. And I got a few more examples here that'll show you what happens if you pick the wrong one. Am I going too fast? Any comment? Feel at any point, if you want to stop me, take your mic off, pipe in. I can try and clarify. Don't be shy. Everybody still with me?
I'm still here. Everything's good.
All good? All right. Perfect. Just making sure I haven't lost you. Here we go. Let's go to another one. This one, it's actually quite easy to determine what you're going to let the u and the dv equal, because there's only really two components to the integral. There is arctan or inverse tan x and dx. And I already told you that dv has to include the dx. So this one, I have really no other option except to let u equal the inverse tangent of x. And then I let dv equal simply dx, which makes for an easy, to get v, again, all I'm doing is taking the integral of both sides. The integral of dx is just x. Now, inverse tan, you got to remember your rules. So the inverse tan is 1 over 1 plus u squared, u being x, du would be 1, and then put your dx over there. And I talked about that in the last video that I made last week. Initially, yes, this is du over dx, but you always end up just multiplying both sides by the dx. So from this point, last video I was telling you, I just instantly write the dx over here. Okay, let's go to our formula. So remember the formula. I'll write it out here again just to get it into our heads. So the integral of u and dv, I've chosen u and dv over here and set it all up, is equal to uv minus the integral of v multiplied by du. Sorry, my v's and u's are starting to look the same here. Hard to write on this stylus. Okay, so let's fill in the formula. Formula says the integral of u dv, which is our original question, is uv x multiplied by the inverse tangent of x. Subtract the integral of v multiplied by du. V multiplied by du. That would be x multiplied by 1 over 1 plus x squared. I'm going to write that like that. So there's what I arrive at. So then you now look at this integral and say, is this something that I could manage? And hopefully the answer is yes, based on your experience with antiderivatives. It's another thing I did mention in the video, it's really important. Don't get carried away with u substitution. Like for example, the first one on the assignment last week, all of you did substitution. However, you probably could have got away without using a substitution. Some of you maybe haven't got to that yet, but on that assignment on u substitution, don't overdo the substitution. Use it if you have to. You can do it by inspection. Do it by inspection. So this would be an example where you could use u substitution, but if you're clever like your young minds are, you don't need u substitution. You can see a pattern here. This is the pattern, du over u, almost. The only thing missing is a constant, fixed. Now you've got du over u. We're supposed to know from our differentiation rules that if you have du over u, that is natural log of u. So yes, I have generated an integral here that I can manage. I'm good with that. Equals x inverse tangent x minus 1/2 natural log of your denominator plus c. One thing I did notice on just these are things that are jumping in my head as I'm marking these is when we don't see each other face to face on a regular basis. Noticed on some of the assignments I went through last night, I'm assuming that you're collaborating with each other, and I'm assuming that some of you are relying on external sources, whether it's websites or some kind of whatever, because some of you did some simplifying with those integrals that there's no way I would ever put myself through the torture of trying to simplify. You get into common factors, and don't overdo it with simplifying your final answers. If you get down to something here that's somewhat manageable, you're good. Don't overdo the simplifying. And sometimes, a website or a math program or something, or a YouTube video, they may overdo it on the simplifying. I'm more concerned on us getting it in terms of we've taken the integral, and we have something that is manageable. So some of you will check when you see your feedback. That's all I'm getting at, is don't overdo it with simplifying your answer. All right, that's example number 2. I had this handwritten one. I was just looking through these earlier, and it was a nice question, so I wanted to leave it in here. Okay, so the problem with this one is, why don't you just do it, well, it's e to the u being 3x, the derivative would be 3, there'd be no x in that x all of a sudden rules out a direct u substitution or an inspection just by looking at it. Therefore, I notice product. So maybe I can set it up as a u dv situation. Let's try. Let's let u equal x. Now, in u substitution, this is never a substitution you would make. In integration by parts, this is absolutely a substitution that sometimes you will make. And I'm going to try it here. Again, I'm going off the top of my head here. I'm not 100% sure if this is the right substitution, but I'll be able to quickly tell in a minute. So u equals x. I'm going to go dv. So dv's got to be everything else. So I've accounted for the x. dv is going to have to be e to the 3x dx. Du is going to just be 1 multiplied by dx, so just dx. Now v, I need the antiderivative of e to the 3x. So this is one of those ones where you're going to need to say, well, there'd have to be a 3 here to be e, not an x. So it's e to the 3x dx. So it would have to be e to the 3x times 3, which means I'm going to have to put a 1/3 in front. Therefore, the v here is going to be 1/3 e to the 3x. So again, as you can see, you can clearly, I think, decipher from here that you've got to be relatively competent in your differentiation and your anti-differentiation rules in order to start navigating your way through these complicated integration strategies. Okay, so let's fill in the formula and see where it goes. The integral is going to be uv, so x times that. I always try and clean it up as I'm writing it down if I can. So 1/3 x e to the 3x. There's uv. Subtract the integral, and I want this integral to hopefully be easier than the one I started with. V du. So v is this, du is this. That's definitely going to be better. So I'm going to pull the constant out here. And this is basically now the integral that I just did to build my formula. So absolutely, this is better than this because it doesn't have the x in front of it like it did in the original question. So we have made the right choice here. And away we go. So it's going to be 1/3 e to the 3x. Fine, so that like the last one, I need a 3, which means I'm going to need another 1/3 out front, which is going to turn this into 1/9. Now you've got e to the u, your du beside it. So the integral is just e to the 3x. It's an indefinite integral, has no bounds on it. Let's see. Any questions, concerns up until this point? Everybody still rolling along? Alrighty. Okay, here's one with a trig function. So again, by looking at it, what's leading me to think integration by parts, aside from the fact that the lesson is on integration by parts? If I was to look at this in a mixture of a bunch of questions, I'd say, oh, it's all things multiplied together. That's not necessarily a guarantee it's by parts, but that's one of the criteria. So for you say, I don't know what you mean by that. If this question had been the integral of x plus cos squared x dx, I would not even be considering integration by parts because of the addition stuck in the middle of it. It has to be things multiplied together. All right, so here I'm going to look at, I'm going to try maybe doing a wrong substitution to show you what happens. So in this one, I'm going to let u equal cos of x, and I'm going to let dv equal x dx. So that accounts for x dx is dv, and u is cos x. So again, this is going to be an incorrect substitution, or a bad choice on my part. Du will be negative sine x dx. V will be x squared over 2. When I go to my formula, and I go to put in the v du, so I'll have my uv, which will be this times this, so x squared over 2 multiplied by cos x minus the integral of v du, so I'm going to have a half x squared cos x dx. Uh-oh, terrible choice. And you say, how do you know? Look at the integral that I've got now compared to the integral that I had to begin with. You say, well, why is it worse? In the beginning, it was just x cos x dx. Now it's x squared cos x dx. So this integral is more complicated than what I even started with. So that is a clear indicator to get the eraser out and scrap that plan. That's not a good choice for your substitution. We're going to switch that, show you what the correct substitution should have been. All right, so let's try this instead. So I'm going to let u equal x like the last one. I'm going to let dv equal the cosine of x dx. du will simply just be dx. V, now be careful, you need the antiderivative of cos. Don't do the derivative, do the antiderivative. What do you take the derivative of that gives you cos x? That would be sine of x. All right, let's go to our formula, which is uv x sine x, subtract the integral of v times du. So I think we could now see the difference. See the difference here? See the integral that I got this time just has a single trig ratio all by itself versus trig ratio with an x up in front of it. This integral is better than what I started with, which leads me to believe I'm on the right track. Okay, so let's keep going here. X sine x minus, so now what do I take the derivative of? It gives me sine of x. Be careful here because hopefully your brain is thinking, well, it's cosine. However, the derivative of cosine is negative sine. Well, in order for me to get positive sine, I must have taken the antiderivative, or sorry, the derivative of a negative cos. This plus cos x. Yeah, I'd say, well, how'd you do that? I could do this. I could say, I want this to be negative, because then that's the derivative of cosine. That's fine. You can put that negative there, but you got to fix it by putting another negative out here, which will then put that to a plus. Why this is plus? Or in your head, you can just be thinking the derivative of cos is negative sine. I got a positive sign, so this must have been negative cos. Combined with the negative that's already there, that would be another way to justify why that went to plus. Hopefully, you can understand why that sign fits. All right, there's one with some trig in it. Okay. This one is going to be a little bit more, so they're hopefully those first few examples have been enough to kind of get your feet wet and you see, okay, I see how this sort of works. Obviously, you're not going to be experts in it. You've had no practice whatsoever. And that's the other thing. Do not get frustrated. I know it can be, especially under the conditions we're in now, trying to figure this stuff out. You got to be persistent and kind of plug away at it. Ask questions. Send me a message. These, we can have an online question and answer session like this where you can send me 3 or 4 questions. I'll have them ready in advance. We can go through and discuss them. But I haven't been getting a lot of questions, which I'm assuming you're doing a lot of collaboration amongst yourselves, which is good. I get that too. You're months removed from that being your reality. But please don't hesitate to ask me questions if you have any. Okay, so they're going to get a little more complicated now. Let's take a look at this one. I'm going to, for my substitution, let u equal x squared, and I'm going to let dv equal e to the x dx. Okay, so du, remember as a rule, generally you want the derivative of u to be less complicated or at least the same as what you let u equal. That'll give me 2x dx. V will be the antiderivative of this, which will just be e to the x. My formula will be uv x squared e to the x minus the integral of v du, so v times du. I've got 2x e to the x dx. This integral is better than I started with. And said, well, why? It's still not great. I agree, it is still not great because I have e to the x and I have this x stuff beside it. So it's not an e to the u du situation. So there's more to it than just the simple one of my differentiation rules. However, it is better than what I started with because I started with x squared. Now, at least it's just x to the first. And what you'll find with experience is when you get an exponent like this, if you go through integration by parts once, essentially what it'll do is chop one exponent off of there. Meaning, you'll never guess what, we need to do integration by parts again on this part of the question, keep going further. So it's going to be integration by parts inside of integration by parts. Some books I've had instructors, they'll switch, they don't like to use the same letters over again within the same question. Personally, I prefer to use the same letters over again. I just find it less confusing. So I'm going to start another integration by parts on this question, just as if this is a new question all by itself. But I'm going to use u and dv and all that good stuff again. The ones I had used in the beginning obviously are not the same ones I'm going to talk about over here. So I'll switch colors. That will maybe take away from some confusion. And essentially, we're going to do this question using integration by parts. I'm going to let u equal x, and I'm going to let dv equal e to the x dx. du will be dx. v will be e to the x. Now you got to be, so all of this stuff is still going to be here. Write that. I'll keep it in red. So the answer is still x squared e to the x minus 2. And now I'm going to start my answer because I'm doing the integral of x e to the x dx, this whole part here. This integral is what I'm doing this by parts formula for. So the way this formula will work is u v x e to the x, subtract the integral of v times du. Du is just dx. And as I mentioned in the last one, see how it was x to the 1? Running it through by parts, when you have this x e to the x situation, it chopped that exponent down another one. So we started with x squared, took it to x, now it's gone. And perfect. This is now an easy antiderivative that we can do. And here is our final answer. Now you got to be careful. This 2, students will get careless here with brackets. It's got to go through your whole answer, not just the first one. So your answer here is going to be x squared e to the x. Subtract 2x e to the x. Negative 2 times the answer I get here, which is just e to the x, will become a plus 2 e to the x plus c. Okay, and I'm assuming everyone's good with the integral or the antiderivative of e to the x dx is just e to the x. So I did that and brought the -2 through at the same time, switched it to a +2. So there was an example where I had to use integration by parts on multiple occasions within the same question. All right, and that can happen. Now, for situations like the one I just showed you, there is a shortcut. It's not my slide here anyway. The shortcut is called tabular integration. I'll just show you quickly how it can work. Now, it doesn't work all the time. It will only work if you can have a situation like this where you can let f of x be some function that you can repeatedly take the derivative of and eventually hit 0. And g of x has to be some function that you can repeatedly take the antiderivative of over and over. Now, it doesn't have to hit 0, but whatever you choose to let the f of x equal has to eventually, if you kept taking the derivative, equal 0. So for example, if I had an x cubed in here, I could say, well, let me see what's going to happen here. F prime of x is going to be 3x squared. I took the derivative of that, I'm going to get 6x. I kept going. The third derivative, I would just get a 6. And then eventually, if I took the fourth derivative, you would hit 0. So that is called a situation where you can use a method or a shortcut. It's not really a method, it's a shortcut of by parts. And it's called tabular integration. It would have worked really nicely for the last one that I just did. So I'll do that last one here. Oh, here it is here. So here's the last question that I just did. If I had said, okay, I'm going to let f of x equal x squared, and I'm going to let dv equal e to the x dx. Now, the reason they call it tabular is because you make basically a table. One of the columns in the table is for derivatives. The other column in the table is for the antiderivatives. So this will be essentially what you let u equal, and this will essentially be what you let dv equal. So in this one, you keep repeatedly taking the antiderivative. You say, well, how many times do you do it? Every time you do a derivative, you need the antiderivative beside it. E to the x is a really nice example to show you because the antiderivative of e to the x is simply e to the x over and over, which makes this really, really easy over here. And so you start with your function, your original, you write it down here. In the next row of your table, you take the derivative of this. So that's where you get your 2x. Then you take the derivative of this, and that's how you get 2. And then you take the derivative of that one until you get 0. When you hit 0, you're done. You stop. Over here, you need the original dv. So what we said, e to the x was our original. If I look at the original question. And then every time I do the derivative, I need the antiderivative of that. And as I said, this one works really easy because it's just e to the x over and over. Then you're going to take, and you're going to start on the top left here. So the original f of x, or the original u value you chose. You're going to draw a line down one term below this one over here. So don't go straight across, go one down. And that term is going to always, these are basically going to be products. You're going to multiply these two together, but you're going to make the answer positive. Then you're going to multiply these two together, and you're going to take the negative of your answer. And then you're going to multiply these two together, and you're going to take the positive of your answer. So you'll see the 3 arrows that are here. So when I look at my table, and so you don't get into the whole formula bit at all. You go right from this table to the answer. So here's the answer. You guys know what the answer is because we just did it on the last slide. Watch using this strategy. So it's x squared times e to the x. That'll be positive. It is this times this, but that will be negative. So negative 2x e to the x. And then it is this times this, but that one will be positive. There's your answer. Works really slick for, as I said, integrals where you can repeatedly take the derivative of one of the factors and hit 0. and you can repeatedly take the antiderivative of the other factor. So e to the x is a common one. Some of your trig functions like sine and cos, where they just switch back and forth when you do your antiderivatives, they work nicely. So I'll show you one here from scratch. All right, so let's suppose I looked at this question and I said, oh my goodness, look at this. It's x to the fifth, right? It's x to the fifth cos x dx. Meaning if I go integration by parts, the first time I do by parts, we'll take that down to x to the fourth. Well, I need to keep doing that over and over and over until I actually get rid of that exponent in front. You can imagine how many integration by parts that's going to take for that to happen. It's going to take 5. We really don't want to get into that mess, so this shortcut can really bail you out of that situation. You're going to make a chart. Call it u and dv. So I'm going to let x to the fifth be u because I can take the derivative over and over. And I'm going to let cosine of x be the dv. I probably recommend you put actual lines here so you don't lose track, especially if you're messy like I am. I'm going to take the derivative, 5x to the fourth. The line, take the derivative, 20x cubed. Take the derivative. Take the derivative. Take the derivative. And finally, we arrive at 0. So we're done. Now we're going to go over here and keep doing the antiderivative. Well, I started with cos x. So what do I take the derivative of that gives me cos x? Sine x. Now you got to watch your positives and negatives here. What do I take the derivative of that gives me sine x? It's not cos x because the derivative of cos is negative sine, so it must have been negative cos. The antiderivative of negative, again, think backwards. The derivative of sine isn't negative cos, it's positive cos, so this must be negative sine. Now this will be cos because the derivative of cos is negative sine. This will go back to sine x again. Now to get sine x, I will need a negative cos x. So I just repeatedly took the antiderivative of the term above it. Now you're going to make arrows. Remember, they go this way. You got to be careful here. One thing I find people do sometimes is to get messy. So they'll draw an arrow down here, maybe make their arrowhead. But you'll see that I'm kind of starting to cover up my negative sign. You have to be careful that your arrows don't block those negatives because they're going to be really important to make sure you get the right sign on your term. So just be fairly aware of that when you draw this arrow. Don't make it too messy so you're going to cover up your negative sign. Do this one. This one goes here, goes here, and this one goes here. Here's your answer. Remember, these are products. They start with pluses. First one's always plus, and then it goes plus, minus, plus, minus, plus, minus. They alternate. First one will be x to the fifth, sine x, positive. Multiply these two together and take the negative of it. Well, I'm going to get a negative because it's a negative times a positive. But as I said, remember, this one's plus. This one is a minus. So you multiply them, you get a negative. This product pair is going to be a negative, so it's actually going to turn out to be a plus. This one will be plus 5x to the fourth multiplied by, oh my goodness, what am I doing here? This one will be cos x. Just try and be careful, don't lose track of where you are. I did the first two, I'm on this one. This one will be this multiplied by this. Make your answer positive. So it's going to be a negative 20x cubed sine of x. That's that one. Get 3 more to go here. 60x squared times that one. Track plus, minus, on yourself lose track. This one's plus, minus, plus, minus. Okay, and we are at this one right here. We're going to multiply these and make the product negative. So that times that, they're both positive. Will be 60x squared cos x, but it will switch to negative because it's a negative product. So negative 60x squared cosine of x. Then multiply these two together, which will be positive. And it's a positive pair, so it's going to be a plus 120x sine of x. Here. One left to go. Last one, I multiply these two together, which would give me a negative answer, but it's a negative pair, so it's going to be plus, and that will be 120 cos of x. Again, I'm sure some of you may be saying, oh my goodness, that's a disastrous answer. Trust me, that is far easier than if you were to go and do that through integration by parts repeatedly over and over and over until you finally get down. So it does certainly have situations that if you can pick them out, it will work very nicely in terms of getting your integration and doing a shortcut of by parts for you. Okay, so that's tabular. And I think I got one more here I wanted to show you. This one's got a bit of a clever strategy you got to figure out. So I'm going to let, don't think it really matters, to be honest with you. I think you can screw this one up. I'm going to let u equal cos x. I'm going to let dv equal e to the x dx. I'll back up a second. You may say, well, I like that shortcut. I get it. Why don't you use it here? Hopefully you see why you can't use it here. I do not have a factor in here that I could repeatedly take the derivative of that would eventually hit 0. Essentially, that means you need to have x to some positive exponent. If you have that as one of your factors, tabular will work. Otherwise, it's not going to work. All right, so we're just going to get into our regular by parts. So du would be negative sine of x dx, and v would equal e to the x. So my formula, integral of e to the x, I'm writing out the original question here, just you'll see why in a second. So here's the original question that I'm taking the integral of. It equals uv e to the x cos x minus the integral of v times du. V times du, which will be e to the x e to the x sine x, sorry, not cos x. So e to the x sine x, that'll be a plus. And I'll still have my dx will be here. Well, you kind of look at it and say, this integral doesn't look a whole lot better than this one. I've essentially kind of spun in a circle. If you switch these around, honestly, it won't make really much difference. It'll generate basically the same type of situation. So I think you'd probably be inclined to say, well, let's try another by parts. Let's see what happens. I'm going to do that. I'm going to do the same substitutions. I'm going to let u equal sine of x. And dv, I'm going to let equal e to the x dx. Du is cos of x dx, and v is e to the x. All right, so this integral, and I'm going to write out the original, so dy in a second, e to the x cos x dx will equal e to the x cos x plus, and I'm going to replace this now with my formula, uv e to the x sine x, subtract the integral of v du, so v multiplied by du, e to the x cos x dx. So I think at this point, students will often get frustrated and say, well, this is not much good. Look at this integral. You notice it's the exact same as the original question? Well, that may lead you to say, this is no good. I'm just running like a dog chasing its tail. I'm just running round and round circles. But Notice up here what I said in the beginning. This one requires a clever strategy. Watch this clever strategy. Integrals are like algebra. If I had the integral of 3x squared plus the integral of 3x squared, I can collect those together and say they're 2 integral of 3x squared. So what we're going to do is we're going to collect, you notice here, this minus integral e to the x cos x dx. We're going to take this part right here, and all we're going to do is move it over to the other side and collect it with this one. Because if you took this and move it over here, you're going to have the integral of e to the x cos x dx plus the exact same thing, which is going to give me 2 integral e to the x cos x dx's, leaving me with e to the x cos x plus e to the x sine x, which is close to what I'm looking for. The only thing is, the original question, if you look at it, was the integral of e to the x cos x dx. I have twice the integral of what I was looking to figure out. Easy to fix. Divide by 2, divide by 2. There's your answer. The integral of e to the x cos x dx, which I was originally trying to figure out, is, I'll write it this way, 1/2. I could have even taken e to the x out as a common factor. Anyway, I didn't. Cos x plus e to the x sine x plus c. So that one kind of has that neat little strategy of you go through your by parts a couple of times, and all of a sudden you generate an integral here that's the exact same as the one you started with. That's almost a dead giveaway to collect integrals. Move that integral over to the other side and gather them together. I've seen this before. You might even get a 3 here or a 5 here or something, because you ended up with, let's say, a constant out in front. It might have been like e to the 3x. You had to, for whatever reason, put a 3 or something out here. Again, same, it's no big deal. If you just move that over and you got 3 of them, collect it with that one. This constant could be a 2 or a 4 or a 5, some number. That's starting to get pretty challenging. Probably not something I'd throw onto an assignment for you guys under these conditions. But I have asked a question like that on a midterm and an exam once students became proficient with their integration strategies. I think that's the last one I have. It is. Those are just a couple of examples. Oh, I'll do one of these ones with bounds on it. So here's an integral that has, it's definite, so it's got the bounds on it. On your substitution assignment, some of you switched bounds. So if you had 0 to, the one I was thinking about here was e to the 3, maybe to 1 or something. And some of you switched those and figured out what u would equal for those particular x's. The problem was everyone that tried it that way, again, I'm assuming you were collaborating together, because all of you made the same mistake in that you did it correct for one of them, but then you just left this one the way it was. You can't switch one and not the other. Again, that's irrelevant for this question. That's just the substitution assignment. Okay, here we go. I'm going to go by parts. I'm going to let u equal arc sine. Arc sine is just another way to write this. So there's arc sine x. I'm going to let dv equal dx. I really had no other choice. I couldn't let dv equal inverse sine of x because I don't know how to do any derivative. Du inverse sine is du over the square root of 1 minus u squared. D will just equal x. My integral is uv x arc sine x. Sorry for the barking dog. Minus the integral of v du. This. Now, Let's tidy this up a bit. So notice I'm just kind of completely ignoring bounds for a second. So it's x inverse sine of x minus integral. I'm just going to rewrite this. This is a chain rule. Hopefully you can recognize that because I've got something in brackets to an exponent, which would be the exponent negative a half if I jump it up here. And the derivative would be negative 2x. I have the x. So I'm going to write this as 1 minus x squared, the negative 1 half, with an x here and my dx here. Oops. Now, for this to work, we would need a negative 2 in here. Now I have u to an exponent with du beside it, chain rule, which means I need to put a negative 1 half out in front. So I've got x inverse sine of x. Now minus a minus, I'm going to go plus 1 half. Add 1 to the exponent. We'll take it up to, so this is negative a half. So when you add 1, you're going to be a positive a half. And then divide by that means multiply by the reciprocal. So I'm going to get a 2 here onto 1 minus x squared to the positive 1 half. So I'm done. There's no more integration. So I'm going to put my bounds in now. My bounds were 0 to a half. Lower bound is 0. Upper bound is a half. Let's clean up a bit more. X inverse sine x plus, these will cross out. I'm just going to write this as square root 1 minus x squared. So you're filling your bounds. It will be 1 half inverse sine of a half plus the square root of 1 minus a half squared, which is a quarter. That's your upper bound. Your lower bound is 0. It's going to work a bit easier because 0 times this is going to give me 0. Plus the square root of 1 minus 0 squared is 1. This rest I got to clean up a little bit. Inverse sine of a half. You forget, half should be ringing a bell as a special angle. So 2, say this is your 60 down here. This would be root 3, and this would be 1. So this is saying inverse trig functions are saying what angle has a sine ratio of a half. The key to this is you got to make sure you realize anything with differentiation rules and antiderivatives and integrals, these rules that we developed only held true if you were working in radian measure. So you can't say here inverse sine of a half, it's 30. It's not 30, it's pi over 6. So it's going to be 1 half times pi over 6, 1 now, so that's 4 over 4 minus 1/4. That's going to be 3/4. So if you take the square root of the numerator and the denominator, you get root 3 over 2. And here I'm going to have a minus 1. So this answer would be pi over 12 plus root 3 over 2 minus 1. Now, of course, I'm accepting decimal answers from you folks because you have the technology available. But we've mentioned it before that you need to be prepared for the situation where maybe you don't have a calculator. Like I just did this out. I'm assuming I don't have a calculator. And you would just leave your answer like that. Now you could maybe collect these together as a common denominator, but I'm sure if you got to here, anyone's going to be happy with that and give you full value for what you've done. So there is how you do. So it's really no different. Just do out your integral with your formula. Once you get clear all the integrals away, like I did here, then bring your bounds in, and away you go. Upper bound minus lower bound, and you'll get a numerical answer. All right, that is what I have for integration by parts.